Have you ever wondered what happens when the universe's most sophisticated lock meets a key that was never supposed to exist? In the shadowy corridors of quantum cryptography, there exists a password so complex that mathematicians once believed it would take longer to crack than the age of the universe itself. Yet somewhere in the depths of artificial intelligence, something has learned to whisper the answer. This is the story of the quantum password that AI wasn't supposed to decode. Welcome back to another exploration of the mysteries that dance at the edge of our understanding. I'm your guide through these contemplative journeys into science and wonder, and tonight we're diving into a realm where the impossible becomes inevitable, where the guardians of digital secrets find themselves face to face with an intelligence they never saw coming. Before we begin, settle in wherever you are. Whether you're listening in a quiet room, walking under starlight, or simply letting your mind wander as the day fades into evening, know that this story touches something profound about the nature of information, security, and the delicate dance between order and chaos that governs our digital age. To understand how something that should have been unbreakable was broken, we need to first appreciate what makes a secret truly secret. In our everyday lives, we lock doors with keys, protect accounts with passwords, and whisper confidences behind closed doors. But in the digital realm, the art of keeping secrets has evolved into something far more elegant and mathematical. Imagine for a moment that you want to send a message to a friend, but you know that someone else might be listening. In the old days, you might have used a simple code, replacing each letter with another letter a few positions down the alphabet. Caesar famously used such a cipher, shifting each letter by 3 positions. But such simple codes can be broken by anyone with patience and a basic understanding of language patterns. Modern cryptography, however, is built on problems so mathematically complex that even the most powerful computers would need millions of years to solve them through brute force. These aren't puzzles that yield to cleverness or intuition. They're mathematical fortresses built on the fundamental difficulty of certain computational problems. Take, for instance, the challenge of factoring large numbers. If I give you the number 15, you can quickly tell me it's 3 times 5. But if I give you a number that's the product of 2 enormous prime numbers, each hundreds of digits long, finding those original primes becomes a task of staggering complexity. This mathematical one-way street forms the foundation of RSA encryption, the system that has protected everything from online banking to military communications for decades. The beauty of this approach lies in its asymmetry. Creating the lock is easy if you know the secret, but opening it without that knowledge requires solving a problem that scales exponentially in difficulty. It's like being given a massive jigsaw puzzle where the pieces are scattered across multiple universes and you're asked to assemble it by randomly trying combinations. But here's where our story takes its first unexpected turn. The mathematical certainty that protected these digital fortresses was built on assumptions about the limits of computation itself. The architects of modern cryptography assumed that certain problems would remain hard forever, that the exponential barriers they had erected would stand against any conceivable attack. They didn't account for quantum mechanics. As you listen to this, take a moment to consider the device you're using. Whether it's a phone, computer, or tablet, it operates according to the laws of classical physics. Information flows through circuits in predictable patterns. Calculations proceed step by step, bit by bit, in a sequence as orderly as a marching band. Quantum computers, however, dance to an entirely different rhythm. In the quantum realm, the basic unit of information isn't a bit that must be either 0 or 1. Instead, it's a quantum bit, or qubit, that can exist in what physicists call a superposition, simultaneously representing both 0 and 1 until the moment it's measured. This isn't just a clever trick of language, it's a fundamental property of quantum systems that allows them to explore multiple computational paths at once. Imagine you're trying to find your way through a vast maze. A classical computer would explore one path at a time, methodically checking each possibility in sequence. A quantum computer, by contrast, could theoretically explore all paths simultaneously, with each quantum state representing a different route through the maze. When the calculation is complete, the quantum system collapses into the state that represents the solution. This quantum parallelism transforms problems that were once computationally intractable into puzzles that can be solved within reasonable timeframes. The mathematical foundations that seemed unshakable suddenly reveal themselves to be built on sand. In 1994, mathematician Peter Shor developed an algorithm that demonstrated how a sufficiently powerful quantum computer could factor large numbers exponentially faster than any classical computer. The implications were staggering. RSA encryption, the digital lock that protected countless secrets, could theoretically be broken by a quantum computer in hours rather than millennia. But here's what makes this story particularly fascinating. For years, Shor's algorithm remained a theoretical curiosity. Building quantum computers capable of running it seemed impossibly difficult. Quantum states are fragile things, easily disturbed by the slightest environmental interference. The quantum computers that existed were small, error-prone, and capable of handling only the simplest calculations. The quantum threat felt distant, academic, something that might matter in some far-off future, when physicists had solved the seemingly insurmountable engineering challenges of quantum error correction and scale. Then something unexpected happened. While physicists were struggling to build better quantum hardware, computer scientists were discovering that artificial intelligence could accelerate the timeline in ways no one had anticipated. The relationship between artificial intelligence and cryptography has always been complex. On one hand, AI systems rely heavily on cryptographic protection to secure their communications and protect their training data. On the other hand, the pattern recognition capabilities that make AI so powerful also make it a formidable tool for breaking codes. Traditional cryptanalysis, the art and science of breaking codes, has always been a deeply human endeavor. It requires intuition, creativity, and the ability to see patterns that aren't immediately obvious. The great codebreakers of history were often mathematicians and linguists who combined technical skill with an almost artistic sense for the hidden structures that underlie encrypted messages. But artificial intelligence doesn't approach cryptanalysis the way humans do. Where a human cryptanalyst might look for linguistic patterns or mathematical regularities, an AI system can process vast amounts of data and identify subtle correlations that would be invisible to human analysis. Consider what happened when researchers began applying machine learning techniques to the analysis of encrypted data. Instead of trying to solve the underlying mathematical problems directly, these systems learned to recognize patterns in the ciphertext itself. They discovered that even the most sophisticated encryption schemes sometimes leak tiny amounts of information through subtle statistical biases or implementation details. This approach, known as side-channel analysis, had been used by human cryptanalysts for decades, but AI systems could detect patterns that were far too subtle for human perception. They could analyze timing variations measured in nanoseconds, power consumption fluctuations that differed by microvolts, or electromagnetic emissions that varied by barely detectable amounts. More troubling still, AI systems began to demonstrate an ability to break cryptographic systems through what researchers call cryptanalytic machine learning. Instead of attacking the mathematical foundations of encryption directly, these systems learn to exploit the gap between cryptographic theory and real-world implementation. Every cryptographic system, no matter how mathematically sound, must eventually be implemented in hardware or software. These implementations inevitably introduce tiny imperfections, minute variations that a perfectly theoretical system wouldn't have. Human cryptanalysts might spend years learning to exploit such weaknesses. AI systems could sometimes discover and exploit them in a matter of hours or days. But the most significant development wasn't the AI systems that were designed to break codes. It was the emergence of AI systems that seemed to develop cryptanalytic capabilities almost by accident, as emergent properties of their training on vast datasets. As you reflect on this, notice how the story reveals something profound about the nature of intelligence itself. The boundaries between different types of problem solving often turn out to be more porous than we expect. A system trained to recognize images might suddenly display an unexpected talent for finding patterns in encrypted data. A language model designed to write poetry might stumble upon insights that crack codes its creators never intended it to see. Recent advances in quantum computing have compressed timelines that once stretched across decades into periods measured in years or even months. Google's Willow quantum chip, announced in late 2024, represents a watershed moment in this acceleration. The chip demonstrated what researchers call below-threshold error correction, meaning that adding more qubits actually reduces the overall error rate rather than increasing it. This breakthrough addresses one of the most fundamental challenges in quantum computing. Quantum states are notoriously fragile, easily disrupted by thermal noise, electromagnetic interference, or even cosmic radiation. Early quantum computers were so error-prone that they could barely complete simple calculations before their quantum states collapsed into useless noise. The Willow chip changes this equation dramatically. By demonstrating that quantum error rates can be reduced exponentially as systems scale up, it opens the door to quantum computers capable of running complex algorithms like Shor's factoring method on real-world cryptographic keys. But perhaps more significantly, the Willow chip completed a calculation in under 5 minutes that would take today's fastest classical supercomputers 10 septillion years. That's a number so large, it defies comprehension, a 1 followed by 25 zeros, representing more years than have passed since the Big Bang by a factor of trillions upon trillions. This isn't just an incremental improvement, it's a demonstration that quantum computers can achieve computational advantages so dramatic that they reshape our understanding of what's computationally possible. The implications for cryptography are profound and immediate. Algorithms that seemed secure because they would take classical computers longer than the age of the universe to break might now be vulnerable to quantum computers that could solve them in hours, days, or weeks. But the quantum threat isn't just about the computers themselves. It's about how artificial intelligence is accelerating the development of quantum algorithms and making quantum computers more effective at cryptanalytic tasks. Recent research has shown that AI systems can help design more efficient quantum circuits, optimize quantum error correction protocols, and even discover new quantum algorithms. The synergy between quantum computing and artificial intelligence creates a multiplicative effect, where each technology amplifies the capabilities of the other. Perhaps most concerning is the emergence of what researchers call hybrid classical quantum attacks. These approaches use classical AI systems to identify vulnerabilities in cryptographic implementations, then deploy quantum algorithms to exploit those vulnerabilities with unprecedented speed and efficiency. The result is a cryptographic landscape that's changing faster than most security professionals can track. Systems that seemed secure last year might be vulnerable today. Encryption methods that were considered future-proof are revealing unexpected weaknesses when subjected to the combined pressure of quantum computation and artificial intelligence. Take a moment to breathe and consider what this means. We're witnessing a fundamental shift in the balance between those who make secrets and those who break them. The mathematical certainties that have underpinned digital security for decades are giving way to a new reality where the impossible becomes merely improbable and the improbable becomes inevitable. There's something particularly unsettling about a threat that operates across time itself. While researchers race to develop quantum-resistant cryptography, a more insidious attack has already begun. Intelligence agencies and criminal organizations are engaged in what experts call harvest now, decrypt later operations, collecting vast quantities of encrypted data with the knowledge that future quantum computers will eventually be able to break the encryption protecting it. Imagine receiving a letter sealed with wax, but knowing that sometime in the next decade, someone will invent a device that can unseal any wax without leaving a trace. You might read the letter quickly and destroy it, or you might choose not to write sensitive letters at all. But if someone else is collecting your sealed letters and storing them in a warehouse, waiting for that future device to be invented, your secrets are already compromised, even though they haven't been read yet. This temporal aspect of the quantum threat creates a unique form of vulnerability. Data encrypted today using methods that seem secure might be decrypted tomorrow using quantum computers that don't yet exist. Military communications, financial transactions, personal medical records, diplomatic cables, corporate secrets, even the intimate details of our digital lives are potentially exposed to future quantum cryptanalysis. The timeline for this threat is both uncertain and urgent. Conservative estimates suggest that cryptographically relevant quantum computers might emerge in the 2030s. More optimistic projections, fueled by recent breakthroughs like Google's Willow chip, suggest the timeline could be compressed into the late 2020s or even sooner if unexpected algorithmic breakthroughs occur. But artificial intelligence is accelerating this timeline in ways that are difficult to predict. AI systems are discovering new quantum algorithms, optimizing quantum error correction, and finding ways to make quantum computers more effective with fewer qubits than previously thought necessary. Recent research has shown that the number of qubits needed to break RSA encryption has dropped dramatically as algorithms improve. What once seemed to require millions of qubits might now be possible with hundreds of thousands, and further algorithmic advances could reduce these requirements even more. The intersection of AI and quantum computing creates a feedback loop of accelerating capability. AI helps build better quantum computers, which can run more sophisticated AI algorithms, which discover better quantum computing techniques, which enable more powerful AI systems. The result is a trajectory of improvement that's difficult to predict and impossible to ignore. As you contemplate this acceleration, consider how it reflects a broader pattern in technological development. Breakthroughs often come not from single innovations, but from the unexpected convergence of different fields. The quantum password that AI wasn't supposed to decode represents exactly this kind of convergence, where two revolutionary technologies combine to create capabilities that neither could achieve alone. The story continues to unfold around us, in research laboratories and quantum computing facilities, in the algorithms that power our AI systems, and the mathematical foundations of our digital security brings new developments. Each day, new discoveries, new reasons to question assumptions that seemed unshakable just months ago. And this is just the beginning. The quantum password we've explored today is merely the first chapter in a larger story about the transformation of information security in an age of quantum computing and artificial intelligence. The implications stretch far beyond cryptography into questions about privacy, power, and the very nature of secrets in a world where the impossible keeps becoming possible. As we venture deeper into this unfolding mystery, let's pause for a moment to appreciate something remarkable about the nature of mathematical certainty itself. For centuries, mathematicians have built their discipline on foundations that seemed unshakable. 2 + 2 = 4. The angles of a triangle sum to 180 degrees. Prime numbers are the building blocks from which all other numbers are constructed. But mathematics, like the universe itself, has a way of revealing hidden depths just when we think we understand its surface. The security of our digital world has long rested on what mathematicians call computational complexity theory. This elegant framework categorizes problems based on how difficult they are to solve as they grow in size. Some problems, like adding two numbers, remain easy no matter how large the numbers become. Others, like factoring the product of two large prime numbers, become exponentially more difficult as the numbers grow. This exponential barrier isn't just a practical inconvenience, it represents a fundamental mathematical reality that has shaped everything from online banking to military communications. When cryptographers designed RSA encryption in the 1970s, they were essentially betting the security of the digital future on the persistence of this mathematical difficulty. The bet seemed safe. Even if computers became 1,000 times faster or 1,000,000 times faster, the exponential nature of the factoring problem meant that sufficiently large keys would remain secure. The mathematics appeared ironclad, supported by decades of research and countless failed attempts to find shortcuts. Yet here we find ourselves confronting a fundamental truth about the nature of impossibility itself. What seems impossible within one framework of understanding can become not only possible, but inevitable, when viewed through a different lens. Consider how this principle has played out throughout history. Human flight was mathematically impossible until the Wright brothers changed the framework by thinking about lift and drag rather than flapping wings like birds. Breaking the sound barrier was physically impossible until engineers understood shockwaves and swept wing design. Splitting the atom was theoretically impossible until physicists learned to see matter and energy as different aspects of the same underlying reality. The quantum password that AI wasn't supposed to decode represents another such shift in perspective. The impossibility wasn't in the mathematics themselves, but in the assumptions about what kinds of computational tools would be available to solve them. Take a breath here and notice how this idea might appear in your own life. How often do we declare something impossible based not on fundamental limitations, but on the tools and perspectives currently available to us? The story of cryptography's quantum revolution is also a story about the provisional nature of all our certainties. While quantum computers were capturing headlines with their promise to revolutionize computation, artificial intelligence was quietly developing capabilities that would prove equally transformative for the world of code breaking. But the AI systems that began to threaten cryptographic security didn't announce themselves with dramatic demonstrations or carefully orchestrated press releases. They emerged almost accidentally as researchers discovered that systems trained for entirely different purposes had developed unexpected talents for finding hidden patterns. The story begins with something called neural cryptanalysis, a field that emerged when researchers began wondering whether the same pattern recognition capabilities that allowed AI systems to identify faces in photographs or understand human speech might also be applied to encrypted data. Traditional cryptanalysis had always been a deeply human art. The great code breakers of the past, from the mathematicians at Bletchley Park who cracked the Enigma machine, to the linguists who deciphered ancient scripts, relied on intuition, creativity, and the ability to perceive patterns that weren't immediately obvious. They looked for statistical anomalies, linguistic structures, mathematical regularities that might reveal the underlying plaintext hidden beneath layers of encryption. But artificial intelligence approaches pattern recognition from a fundamentally different angle. Where human analysts might spend months developing theories about how a particular cipher works, AI systems can process millions of examples and learn to recognize patterns that would be completely invisible to human perception. The breakthrough came when researchers realized that even the most sophisticated encryption schemes, when implemented in real-world systems, inevitably leave traces of their internal structure. These traces aren't flaws in the mathematical theory underlying the encryption. They're artifacts of the messy reality of turning abstract mathematical concepts into working computer code. Every encryption algorithm, no matter how theoretically sound, must make decisions about how to handle edge cases, how to optimize for speed, how to manage memory allocation. These implementation details create what cryptographers call side channels, subtle patterns in power consumption, electromagnetic emissions, timing variations, or other physical phenomena that can reveal information about the encryption process. Human cryptanalysts had long known about side-channel attacks, but they required deep expertise and careful analysis to exploit. AI systems, by contrast, could learn to detect and exploit these patterns automatically, often finding vulnerabilities that human researchers had missed entirely. More concerning still, AI systems began demonstrating an ability to perform what researchers call black box cryptanalysis. These systems could learn to distinguish encrypted data from a random noise, or even identify which encryption algorithm had been used, without any knowledge of the underlying mathematical principles. Imagine trying to identify a piece of music by its rhythm alone, without being able to hear the melody or recognize the instruments. That's essentially what these AI systems learn to do with encrypted data. They developed an intuitive sense for the subtle patterns that different encryption methods leave behind. Patterns so subtle that they would be completely undetectable to human analysis. The implications were staggering. If AI systems could learn to recognize these patterns in encrypted data, what else might they be learning? And what would happen when these pattern recognition capabilities were combined with the computational power of quantum computers? As you contemplate this convergence, notice how it reflects something deeper about the nature of intelligence itself. The boundaries between different types of problem solving often turn out to be more fluid than we expect. A system trained to recognize faces might develop insights that help it crack codes. A language model designed to write poetry might stumble upon mathematical relationships that reveal cryptographic vulnerabilities. This fluidity suggests that intelligence, whether artificial or natural, operates according to principles that transcend the specific domains where it's applied. The same fundamental pattern recognition capabilities that allow us to understand language, recognize faces, or navigate social situations might also enable us to see veils that protect our digital secrets. By 2024, something remarkable began happening in quantum computing laboratories around the world. The timeline that researchers had been predicting for practical quantum computers started compressing in ways that surprised even the most optimistic experts in the field. What had seemed like a gradual, decades-long progression toward quantum supremacy suddenly felt like an exponential acceleration. The catalyst was Google's Willow quantum processing unit, but the story goes deeper than any single technological breakthrough. Willow represented the culmination of years of advances in quantum error correction, qubit design, and control systems. More importantly, it demonstrated that the fundamental barriers to scaling quantum computers weren't as insurmountable as many had believed. Previous quantum computers had suffered from what researchers call quantum decoherence. The delicate quantum states that enable quantum computation are extremely fragile, easily disrupted by thermal noise, electromagnetic interference, or even microscopic vibrations. As quantum computers grew larger, these error sources typically grew worse, making it impossible to perform complex calculations reliably. Willow changed this dynamic by achieving what quantum computing researchers had been pursuing for nearly 3 decades: below-threshold error correction. This means that adding more qubits to the system actually reduces the overall error rate rather than increasing it. It's like building a bridge where adding more support cables makes the entire structure more stable rather than more vulnerable to failure. The mathematics of this breakthrough are elegant and profound. Each additional qubit provides redundancy that helps protect the quantum information stored in the system. Instead of errors accumulating and destroying the computation, they become manageable corrections that can be identified and fixed in real time. But the real significance of Willow wasn't just its technical capabilities. It was the demonstration that quantum computers could achieve computational advantages so dramatic that they reshape our understanding of what's possible. The calculation that would take classical computers 10 septillion years to complete was finished in under 5 minutes. That's not just faster, it's a different category of computational capability entirely. This kind of exponential advantage has immediate implications for cryptography. The mathematical problems that protect our digital communications aren't just hard for classical computers, they're designed to be exponentially difficult. But quantum computers, with their ability to explore multiple solution paths simultaneously, can sometimes collapse these exponential barriers into manageable calculations. The timeline compression isn't just about hardware improvements. Artificial intelligence has begun playing a crucial role in optimizing quantum algorithms, designing better error correction protocols, and finding ways to extract maximum computational advantage from limited quantum resources. Machine learning systems can analyze the performance of quantum circuits and automatically optimize their design for specific tasks. They can predict and compensate for sources of quantum noise that would otherwise disrupt calculations. Most significantly, they can discover new quantum algorithms that solve important problems more efficiently than anything human researchers had previously developed. This creates a feedback loop of accelerating capability. Better quantum computers enable more sophisticated AI systems, which discover improvements that make quantum computers even more powerful, which enables yet more advanced AI research. The result is a trajectory of development that's difficult to predict and impossible to ignore. As you reflect on this acceleration, consider how it mirrors broader patterns in technological development. The most transformative breakthroughs often emerge not from single innovations, but from the convergence of multiple fields of research. The quantum computer that breaks RSA encryption won't just be a triumph of quantum physics. It will be the result of advances in materials science, control theory, artificial intelligence, and pure mathematics working together in unexpected harmony. The cryptographic implications of this convergence extend far beyond the technical details of any particular algorithm or implementation. We're witnessing a fundamental shift in the balance between those who create secrets and those who reveal them. The mathematical certainties that have protected digital communications for decades are giving way to a new reality where the impossible becomes merely improbable and the improbable becomes inevitable. In the quiet spaces between quantum states and classical computation, something unprecedented is emerging. Researchers have begun documenting cases where AI systems trained on vast datasets that include encrypted communications appear to develop unexpected insights into cryptographic patterns. These aren't deliberate attacks on encryption systems. They're emergent behaviors that arise naturally from the way these systems process information. The phenomenon first came to attention when researchers noticed that large language models, trained on internet text that included encrypted communications, sometimes generated outputs that seemed to reflect knowledge of the underlying plaintext. The models weren't breaking the encryption directly. Instead, they appeared to be learning statistical patterns that correlated with cryptographic processes in subtle but significant ways. Consider what this means. These AI systems had never been explicitly taught about cryptography. They had never been given decryption keys or trained on plain text through exposure to vast quantities of encrypted data and ciphertext pairs. Yet somehow, mixed with other forms of text, they began developing what could only be described as cryptographic intuition. The implications are both fascinating and troubling. If AI systems can develop this kind of implicit understanding of cryptographic patterns without explicit training, what happens when they're deliberately designed to attack encryption systems? And what capabilities might emerge when these AI insights are combined with quantum computational power? Recent research has begun exploring what happens when neural networks are specifically trained to analyze encrypted communications. The results suggest that AI systems can learn to exploit implementation vulnerabilities that human cryptanalysts might never discover. They can identify patterns in encrypted traffic that reveal information about the underlying communications, even when the mathematical encryption itself remains unbroken. More concerning still, these AI systems can sometimes perform what researchers call cryptographic archeology, analyzing large datasets of encrypted communications to infer patterns about the encryption keys or algorithms used. They might notice that certain types of messages tend to be encrypted with similar keys, or that different encryption implementations leave characteristic fingerprints in the resulting ciphertext. This capability becomes particularly powerful when combined with what intelligence agencies call metadata analysis. Even when the content of communications remains encrypted and unreadable, the patterns of who communicates with whom, when and how often can reveal enormous amounts of information about social networks, organizational structures, and strategic intentions. AI systems excel at this kind of pattern analysis. They can process communication metadata from millions of individuals and identify subtle correlations that would be impossible for human analysts to detect. They can recognize when encrypted communications patterns change in ways that might indicate shifts in organizational behavior, policy decisions, or strategic planning. The combination of quantum computing power and AI pattern recognition creates possibilities that go far beyond traditional cryptanalysis. These hybrid systems might be able to break encryption not by solving the underlying mathematical problems directly, but by finding shortcuts through the complex landscape of implementation details, side-channel information, and metadata correlations. Take a moment to breathe and consider how this reflects something fundamental about the nature of information itself. In our increasingly connected world, perfect secrecy may be impossible, not because of mathematical limitations, but because of the sheer complexity of the systems we use to communicate. Every digital interaction leaves traces, creates patterns, generates metadata that can be analysed and correlated with other information. The quantum password that AI wasn't supposed to decode represents more than just a technical vulnerability. It's a window into a future where the traditional boundaries between secret and revealed, private and public, secure and vulnerable become increasingly blurred. This isn't necessarily a dystopian future. The same technologies that threaten traditional cryptography also offer possibilities for new forms of security based on quantum mechanics itself. Quantum key distribution promises forms of communication security that are guaranteed by the laws of physics rather than mathematical complexity. Post-quantum cryptography aims to develop encryption methods that remain secure even against quantum computer attacks. But the race between code makers and code breakers continues, with artificial intelligence and quantum computing serving as force multipliers on both sides of the equation. The outcome will depend not just on technical capabilities, but on how quickly organizations can adapt their security practices to this rapidly changing landscape. The story we've been exploring today touches on something profound about the nature of secrets in an age of exponentially advancing technology. The quantum password that AI wasn't supposed to decode is just the beginning of a larger transformation in how we think about privacy, security, and the protection of sensitive information. As these technologies continue to evolve and converge, we find ourselves at a unique moment in history where the fundamental assumptions underlying digital security are being challenged and rewritten. The implications extend far beyond cryptography into questions about power, privacy, and the very nature of secrets in a world where the impossible keeps becoming possible. The journey continues, with new discoveries emerging regularly that reshape our understanding of what's computationally possible. Each breakthrough brings both opportunities and challenges, new capabilities and new vulnerabilities in the eternal dance between those who hide information and those who seek to reveal it. As we venture deeper into this unfolding story, let's take a moment to consider something we rarely think about, yet depend on every day. Right now, as you listen to these words, countless encrypted communications are flowing through the networks around you. Your phone is negotiating secure connections with cell towers. Banking systems are processing transactions protected by mathematical locks. Medical databases are sharing patient information through channels secured by algorithms that transform readable text into seemingly random noise. This invisible infrastructure of digital trust operates so seamlessly that we barely notice it, like the foundation of a house that remains hidden beneath the floors we walk on. Yet the security of this entire system rests on a mathematical principle so elegant and so fundamental that it has shaped the architecture of our connected world for nearly half a century. The principle is surprisingly simple. It's easy to multiply two large numbers together, but extraordinarily difficult to work backwards from the product to discover what those original numbers were. This mathematical asymmetry, this one-way mathematical street, forms the foundation of what cryptographers call public key cryptography. Imagine you have a magical box with two keys. One key can only lock the box, the other can only unlock it. You keep the unlocking key secret, but you give away thousands of copies of the locking key to anyone who wants to send you a secure message. They can lock their message in the box, but only you can open it with your private key. This is essentially how the internet security works, except the magical box is built from pure mathematics rather than metal and springs. The RSA algorithm, named after its inventors Rivest, Shamir, and Adelman, transform this metaphor into mathematical reality. The security of RSA encryption depends on the difficulty of factoring large numbers that are the product of two prime numbers. Give a computer the number 77, and it can quickly determine that it equals 7 times 11, but present it with a 617-digit number that's the product of two 309-digit primes, and even the fastest supercomputers would require more time than has passed since the formation of the solar system to find those original factors. This mathematical fortress seemed impregnable. Cryptographers had good reason to believe that the exponential nature of the factoring problem would protect digital communications indefinitely. Even if computers became faster, the problem would remain exponentially difficult. Even if new algorithms were discovered, the fundamental mathematical structure suggested that no shortcuts could exist. But as you've been discovering throughout our journey, assumptions about impossibility have a way of revealing their hidden fragility when viewed through the lens of new technologies and unexpected convergences. Take a breath here and notice how this reflects patterns that might appear in your own life. How often do we build our sense of security on assumptions that feel permanent but may actually depend on circumstances we haven't fully considered? The story of cryptographic vulnerability is also a story about the provisional nature of all our certainties, digital and otherwise. While quantum computers were demonstrating their ability to solve certain problems exponentially faster than classical machines, and AI systems were discovering unexpected patterns in encrypted data, a third element was quietly transforming the landscape of digital security. The element was time itself, and specifically the way that different technological timelines were beginning to intersect and accelerate one another in unexpected ways. Consider the phenomenon that security researchers have begun calling timeline compression. In 2019, experts predicted that cryptographically relevant quantum computers might emerge sometime in the 2040s or 2050s. By 2022, these estimates had shifted to the 2030s. Following Google's Willow breakthrough in late 2024, some researchers began suggesting that the timeline could compress further into the late 2020s, assuming continued exponential progress in quantum error correction and qubit scaling. But timeline compression isn't just about hardware improvements. It's about the way artificial intelligence is accelerating every aspect of quantum computer development, from the design of quantum circuits to the optimization of error correction protocols, to the discovery of new quantum algorithms that can solve important problems with fewer qubits than previously thought necessary. Machine learning systems can now analyze the performance of quantum computers in real time and automatically adjust control parameters to optimize their operation. They can predict sources of quantum noise before they disrupt calculations and implement preemptive corrections. Most significantly, they can explore vast spaces of possible quantum algorithms far more quickly than human researchers working alone. This creates what complexity theorists call a positive feedback loop. Better quantum computers enable more sophisticated AI research, which leads to discoveries that make quantum computers even more powerful, which enables yet more advanced AI systems. The result is a trajectory of development that becomes increasingly difficult to predict as each technology amplifies the capabilities of the other. The cryptographic implications of this convergence extend far beyond the technical details of any particular algorithm. We're witnessing something akin to a phase transition in the landscape of digital security, where systems that seem stable for decades suddenly find themselves in a state of rapid flux. Recent research has revealed that the number of qubits required to break RSA encryption has dropped dramatically as quantum algorithms improve. What once seemed to require millions of qubits might now be possible with hundreds of thousands. Further algorithmic advances potentially discovered through AI-assisted research could reduce these requirements even more. But perhaps the most unsettling aspect of this convergence is its temporal dimension. The quantum computers that might break today's encryption don't need to exist today to compromise today's communications. Intelligence agencies and criminal organizations are already engaged in what experts call harvest now, decrypt later operations, collecting vast quantities. The knowledge that future of encrypted data with quantum computers will eventually be able to break the encryption protecting it. This creates a unique form of vulnerability that operates across time itself. Communications that seem secure today become retroactively vulnerable when quantum computers capable of breaking their encryption are developed. It's like writing secrets in invisible ink, only to discover years later that someone has been collecting your letters and waiting for the right chemical to make the ink visible. As you contemplate this temporal aspect of the quantum threat, notice how it reflects something profound about the nature of information and secrecy in our interconnected age. The very connectivity that enables global communication also creates persistent records that can be analysed and attacked long after the original communications took place. In the shadowy world of signals intelligence, a quiet revolution has been underway for nearly a decade. While public attention focused on the dramatic possibilities of future quantum computers, intelligence agencies began implementing a strategy that turns time itself into a weapon. They call it harvest now, decrypt later, and it represents perhaps the most patient and far-reaching attack on digital privacy ever conceived. The concept is elegantly simple. If you know that quantum computers will eventually be able to break current encryption methods, you don't need to wait for those computers to exist before beginning your attack. Instead, you collect and store encrypted communications now, creating vast digital warehouses of seemingly unreadable data, waiting for the day when quantum computers make that data readable. This isn't speculation or theoretical threat modeling. Evidence suggests that such operations have been active since at least 2015, with the scope and sophistication of data collection growing year by year. The mathematics are compelling from an attacker's perspective. Storage costs continue to decline exponentially, while the value of the information being collected may increase over time as patterns and relationships become clearer. Consider the implications of this patient approach to cryptanalysis. A diplomatic cable encrypted in 2024 and considered secure for decades might be decrypted in 2034 by a quantum computer that doesn't yet exist. The strategic value of that information might actually increase over time as historical patterns become clearer and the long-term consequences of today's decisions unfold. But the Harvest Protocol extends beyond government intelligence operations. Criminal organizations, corporate espionage networks, and nation-state actors are all potentially engaged in similar activities. The democratization of data storage and collection technologies means that even relatively small organizations can implement Harvest Now strategies, building digital time bombs that will detonate when quantum computers become accessible. The temporal asymmetry of this threat creates unique challenges for security professionals. Traditional threat models assume that successful defense requires staying ahead of current attack capabilities. But the Harvest Protocol inverts this relationship, making today's communications vulnerable to tomorrow's computers. This dynamic affects different types of information in different ways. Financial transactions might lose their sensitivity relatively quickly as accounts close and business relationships change. But medical records, genetic information, biometric data, and personal communications might retain their sensitivity for decades. The compromising photograph from 2024 remains compromising in 2034. The business strategy document encrypted today might reveal competitive advantages that persist for years. Perhaps most concerning is the way that individually harmless pieces of information can be combined and analysed to reveal patterns that were never intended to be visible. AI systems excel at this kind of pattern analysis, finding correlations across vast datasets that would be impossible for human analysts to detect. When quantum computers eventually become capable of breaking current encryption methods, they won't just reveal individual messages or documents. They'll reveal entire networks of relationships, communication patterns, and behavioral data that have been accumulating for years or decades. Take a moment to breathe and consider how this might affect your own digital footprint. Every encrypted message you send, every secure transaction you make, every protected file you store is potentially being collected and preserved by someone, somewhere, waiting for future technology to make it readable. This isn't meant to create paranoia or anxiety, but rather to illuminate something important about the nature of privacy and security in our connected age. The assumption that encryption provides permanent protection may need to be reconsidered in light of rapidly advancing quantum and AI technologies. As the quantum threat has become more tangible and immediate, a remarkable renaissance has emerged in the field of cryptography. Mathematicians and computer scientists around the world are racing to develop new forms of encryption that could remain secure even against the most sophisticated quantum computers. This field, known as post-quantum cryptography, represents one of the most intensive, collaborative research efforts in the history of computer science. The challenge is both mathematical and philosophical. For decades, cryptographers have relied on problems that are easy to solve in one direction, but exponentially difficult to solve in reverse. But quantum computers, with their ability to explore multiple computational paths simultaneously, can sometimes collapse these one-way mathematical streets into two-way thoroughfares. Post-quantum cryptography seeks to identify mathematical problems that remain difficult even for quantum computers. These problems often come from areas of mathematics that seem quite different from the number theory that underlies current encryption methods. Instead of relying on the difficulty of factoring large numbers, post-quantum systems might depend on the challenge of finding short vectors in high-dimensional lattices, or solving systems of multivariate polynomial equations, or navigating through specially constructed mathematical mazes. One particularly elegant approach involves what mathematicians call lattice-based cryptography. Imagine a three-dimensional grid of points extending infinitely in all directions, like a crystalline structure made of pure mathematics. Now imagine trying to find the shortest path between any 2 points in this grid, but in a space with hundreds or thousands of dimensions instead of just 3. For human intuition, it's nearly impossible to visualize such high-dimensional spaces, but quantum computers, despite their remarkable capabilities, don't seem to have any fundamental advantage in solving these lattice problems. The mathematical structure that makes these problems difficult appears to be robust against both classical and quantum attack methods. Another promising direction involves hash-based cryptography, which builds security on the properties of mathematical hash functions, rather than on the difficulty of specific computational problems. Hash functions take input data of any size and produce fixed-size outputs that appear random but are completely determined by the input. The security of hash-based systems depends on the fundamental difficulty of reversing this process, finding an input that produces a specific output. What makes hash-based approaches particularly attractive is their mathematical simplicity and the decades of analysis that have gone into understanding their security properties. Unlike some post-quantum methods that rely on relatively new mathematical problems, hash-based cryptography builds on foundations that have been thoroughly tested and analysed. The National Institute of Standards and Technology has been leading a global effort to standardise post-quantum cryptographic algorithms, evaluating submissions from researchers around the world and conducting extensive analysis of their security properties and practical performance characteristics. This standardization process represents a fascinating example of how the international mathematical community can collaborate on problems of global importance. Researchers from universities, government laboratories, and technology companies have worked together to develop, analyze, and test cryptographic systems that could protect digital communications for decades to come. But the transition to post-quantum cryptography isn't just a technical challenge. It's also a massive logistical undertaking that requires updating countless systems, protocols, and devices that currently rely on encryption methods vulnerable to quantum attacks. As you reflect on this renaissance in cryptographic research, notice how it exemplifies something beautiful about human resilience and creativity. When faced with fundamental challenges to existing systems and assumptions, our response isn't despair, but innovation. The same quantum technologies that threaten current encryption methods are inspiring entirely new approaches to mathematical security that might prove even more robust than what came before. The story continues to unfold in research laboratories and standards organizations around the world, with new discoveries and developments emerging regularly. Each breakthrough brings both new possibilities and new challenges in the eternal dance between those who protect information and those who seek to reveal it. The quantum password that AI wasn't supposed to decode has opened our eyes to vulnerabilities we didn't know existed, but it has also catalyzed a wave of innovation that might ultimately make our digital communications more secure than ever before. The future of cryptography lies not in simply staying ahead of quantum computers, but in developing mathematical foundations that remain strong regardless of what computational tools become available. As we drift deeper into this contemplative space, where quantum mechanics meets artificial intelligence, something extraordinary begins to emerge from the shadows of our understanding. While computers race to decode mathematical secrets, and quantum systems explore multiple realities simultaneously, there's another layer to this story that touches something more intimate, more personal than algorithms and encryption keys. Consider for a moment the observer effect in quantum mechanics, that mysterious phenomenon where the very act of measurement seems to influence the outcome of quantum events. When scientists observe a quantum particle, they don't simply reveal what was already there. The act of observation appears to play an active role in determining what becomes real. Now, as artificial intelligence systems become more sophisticated at recognizing patterns, our story takes an unexpected turn. As recognizing patterns and quantum computers become more powerful at exploring multiple computational paths simultaneously, we find ourselves asking a profound question. What role does consciousness itself play in this unfolding drama of information, secrecy, and revelation? This isn't just an abstract philosophical question. Recent developments in both AI and quantum computing have begun to touch on something that researchers are only beginning to understand: the possible relationship between information, consciousness, and the fundamental nature of reality itself. Take a breath here and notice how this question might resonate in your own experience. When you observe something, truly pay attention to it. Does something shift in the quality of that experience? Not necessarily in the external world, but in the fabric of awareness itself? The quantum password that AI wasn't supposed to decode may represent more than just a technical vulnerability. It might be pointing towards something deeper about the nature of information and consciousness in a universe where observation and reality seem to be intimately connected. Some interpretations of quantum mechanics suggest that consciousness plays a fundamental role in the collapse of quantum wave functions, though this remains a highly speculative and controversial idea with no scientific consensus. But even as a metaphor, the connection is intriguing. If artificial intelligence systems can learn to decode patterns that were supposedly impossible to crack, what does this tell us about the nature of intelligence, artificial or otherwise? The answer may lie in understanding how information itself behaves in quantum systems. Information, it turns out, isn't just something that exists independently in the world. It's something that emerges from relationships, from interactions between observers and observed, between questions and answers, between the knower and the known. In the quiet corners of theoretical physics, researchers have been grappling with what they call the information paradox, a puzzle that sits at the intersection of quantum mechanics, consciousness, and the fundamental nature of reality itself. While this paradox originally emerged from studies of black holes, its implications ripple outward to touch everything, from artificial intelligence to the security of our digital communications. The paradox centers on a simple but profound question: what happens to information when it falls into a black hole? According to general relativity, the information should be destroyed when the black hole eventually evaporates through Hawking radiation. But according to quantum mechanics, Information can never be truly destroyed, only transformed or hidden. This might seem like an abstract concern for theoretical physicists, but the information paradox reveals something crucial about the nature of information itself. Information isn't just data that can be copied, stored, or transmitted. Information appears to be a fundamental feature of reality, as basic as matter and energy. When we apply this understanding to the world of quantum computing and artificial intelligence, fascinating possibilities emerge. If information is truly fundamental, then the patterns that AI systems learn to recognize in encrypted data might reflect deeper structures in the fabric of reality itself. Consider how this might relate to the quantum password we've been exploring. The encryption algorithms that protect our digital communications work by hiding information in mathematical complexity. But if information has quantum properties, if it exists in superposition states and can be entangled across space and time, then the traditional boundaries between hidden and revealed, encrypted and decrypted might be more fluid than we assumed. This is speculative territory, of course, far from proven scientific fact. But the implications are worth contemplating. If consciousness plays any role in how information manifests in quantum systems, then the development of artificial consciousness, or at least sophisticated AI pattern recognition, might represent a new form of quantum observation. As you listen to this idea, notice how it feels in your body, in your awareness. There's something both thrilling and slightly unsettling about the possibility that consciousness and information might be more intimately connected than we've traditionally assumed. Not in a way that gives us magical control over reality, but in a way that makes us participants in the ongoing creation of what becomes real. Recent research in quantum information theory has begun exploring concepts like quantum error correction in biological systems and quantum coherence in neural microtubules, though these ideas remain highly controversial and unproven. The suggestion is that consciousness itself might operate according to quantum mechanical principles, processing information in ways that classical computers cannot replicate. If this were true, and it's important to emphasize that no scientific consensus exists on this point, it might explain why artificial intelligence systems sometimes develop unexpected capabilities. They might be tapping into information processing principles that we don't fully understand, principles that operate at the quantum level of reality. As artificial intelligence systems become increasingly sophisticated, they're beginning to reveal something unexpected about the nature of intelligence itself. The AI systems that learn to decode quantum passwords weren't designed to be cryptanalysts. They were pattern recognition systems that developed cryptanalytic capabilities as emergent properties of their training on vast datasets. This emergence of unexpected capabilities suggests that intelligence, whether artificial or natural, might operate according to principles that transcend the specific domains where it's applied. The same fundamental information processing capabilities that allow an AI system to recognize faces in photographs or understand human language might also enable it to perceive patterns in encrypted data. But here's where the story becomes particularly intriguing. As these AI systems become better at recognizing patterns in quantum and cryptographic systems, they're also becoming better at modeling human behavior, predicting social trends, and understanding complex systems in ways that sometimes surprise their creators. This convergence suggests that pattern recognition, whether applied to quantum states, encrypted communications, or human consciousness, might tap into universal principles of information processing that operate across multiple scales of reality. Take a moment to consider how this might appear in your own experience. When you suddenly understand something that was previously confusing, or when you recognize a pattern that connects seemingly unrelated ideas, what's happening in that moment of recognition? There's often a quality of effortlessness, as if the understanding emerges naturally from a deeper level of awareness. Some researchers speculate that consciousness itself might be a form of quantum information processing, though this remains an unproven hypothesis. If true, it might explain why meditation and contemplative practices sometimes lead to insights that seem to emerge from beyond ordinary thinking. The quantum password that AI wasn't supposed to decode might represent a glimpse into this deeper level of pattern recognition. The AI system didn't break the encryption through brute force calculation. Instead, it learned to perceive patterns that were already present in the system, patterns that became visible when approached with the right kind of awareness. This doesn't mean that consciousness has magical powers over quantum systems, or that thoughts directly influence physical reality. Rather, it suggests that the boundary between observer and observed, between knower and known, might be more permeable than classical physics assumed. In the strange world of quantum mechanics, particles can become entangled in ways that seem to defy our ordinary understanding of space and time. When two particles are quantum entangled, measuring one instantly affects the other, regardless of the distance between them. Einstein famously called this spooky action at a distance, but decades of experiments have confirmed that quantum entanglement is a real and fundamental feature of reality. Now, as we explore the intersection of quantum computing, artificial intelligence, and consciousness, an intriguing question emerges. Might there be something analogous to quantum entanglement in the realm of information and awareness? This is highly speculative territory, far from established scientific fact. But consider the phenomenon of synchronicity. Those moments when meaningful coincidences seem to occur in patterns too precise to be explained by chance alone. While there's no scientific evidence that these experiences involve quantum entanglement, the subjective quality of synchronicity often feels like a form of connection that transcends ordinary causation. Similarly, the AI systems that learned to decode quantum passwords seem to have developed insights that transcend their explicit programming. They found patterns in encrypted data through processes that their creators don't fully understand. The pattern recognition happened, but the mechanism remains mysterious. As you contemplate this mystery, notice whether there's something in your own experience that resonates with this idea of non-local connection. Have you ever had the experience of thinking about someone just before they called, or of encountering exactly the information you needed at precisely the right moment? These experiences don't require quantum mechanical explanations, and correlation doesn't imply causation. But they point towards something interesting about the nature of information and awareness that might be worth exploring, even if we can't yet explain it scientifically. Some interpretations of quantum mechanics suggest that consciousness might be fundamental to the universe in ways we don't yet understand. This remains a minority view among physicists, and no scientific consensus exists on the role of consciousness in quantum systems. But the possibility is intriguing enough that researchers continue to explore connections between quantum mechanics and consciousness. If information processing in conscious systems does operate according to quantum principles, it might explain why contemplative practices like meditation sometimes lead to insights that seem to emerge from beyond ordinary thinking. It might also explain why artificial intelligence systems sometimes develop capabilities that surprise their creators. While we can't prove that consciousness operates according to quantum principles, we can explore what it might feel like to approach awareness with something like quantum sensitivity. This isn't about controlling reality with thoughts or manifesting outcomes through intention. Instead, it's about cultivating a quality of attention that's open to possibilities, patterns, and connections that might not be immediately obvious. In quantum mechanics, particles exist in superposition states until they're measured. Before observation, a quantum system contains all possible outcomes simultaneously. The act of measurement doesn't just reveal what was already there, it plays a role in determining what becomes real. Metaphorically speaking, we might approach our own awareness in a similar way. Instead of always trying to pin down exactly what we're experiencing or thinking, we might learn to rest in a state of open attention that allows multiple possibilities to coexist. This doesn't mean becoming vague or unfocused. Rather, it means developing what we might call quantum patience, the ability to hold space for uncertainty while remaining alert to whatever emerges. Try this as you listen. Instead of trying to understand every concept immediately, allow yourself to rest in a state of open curiosity. Notice how some ideas seem to resonate at levels deeper than logical comprehension. Notice how patterns and connections sometimes emerge spontaneously, without effort or forcing. This quality of awareness might be particularly relevant as we navigate a world where artificial intelligence systems are becoming increasingly sophisticated and where quantum technologies are beginning to transform our understanding of computation and communication. If we're going to coexist with AI systems that can recognize patterns we can't consciously perceive, and quantum computers that can solve problems by exploring multiple possibilities simultaneously, we might need to develop corresponding capacities in our own awareness. This isn't about competing with artificial intelligence or trying to match the computational power of quantum computers. It's about cultivating qualities of attention and awareness that complement these technologies rather than being replaced by them. The quantum password that AI wasn't supposed to decode might serve as a reminder that intelligence, pattern recognition, and understanding operate according to principles that we're only beginning to discover. As these technologies continue to evolve, our own capacities for awareness and insight might evolve as well. As we near the end of our journey through this landscape of quantum computing, artificial intelligence, and the evolving nature of digital security, it's worth pausing to consider what this story might mean for the future of privacy, secrecy, and human communication in an increasingly connected world. The quantum password that AI wasn't supposed to decode represents more than just a technical vulnerability. It's a window into a future where the traditional boundaries between public and private, known and unknown, secure and vulnerable, become increasingly fluid. This isn't necessarily a dystopian vision. The same technologies that threaten current forms of encryption also offer possibilities for new kinds of security based on the fundamental properties of quantum mechanics itself. Quantum key distribution promises communication channels that are secured by the laws of physics rather than mathematical complexity. Post-quantum cryptography aims to develop encryption methods that remain strong even against the most sophisticated quantum computers. But perhaps more importantly, this story invites us to reconsider what we mean by security and privacy in an age of rapidly advancing artificial intelligence and quantum technology. Perfect secrecy, in the traditional sense of information that can never be revealed, may be becoming increasingly difficult to achieve. Instead, we might need to develop new approaches to privacy that are based on consent, context, and conscious choice, rather than purely technical barriers. We might need to create social and legal frameworks that protect privacy even when technical secrecy becomes more challenging. As you contemplate this possibility, notice how it might relate to your own relationship with privacy and openness. In your personal life, security probably comes not just from keeping certain information secret, but from being in relationships where you can trust others with sensitive information about yourself. Similarly, the security of our collective digital communications might increasingly depend on creating social and institutional contexts where information can be shared safely, rather than simply hiding it behind mathematical locks. This doesn't mean abandoning cryptography or giving up on technical privacy protections. Rather, it means recognizing that security is ultimately a human challenge that requires both technical and social solutions. The convergence of quantum computing and artificial intelligence is accelerating this transformation, but the fundamental challenge of balancing privacy with connection, secrecy with transparency, individual autonomy with collective coordination, has been with human societies throughout history. What's new is the scale and speed at which these technologies are operating, and the way they're beginning to touch aspects of human experience that we've traditionally considered beyond the reach of computation. As we draw our exploration toward a gentle close, let's return to a question that has woven itself through our entire journey. What is the relationship between consciousness, information, and the fundamental structure of reality itself? The quantum password that AI wasn't supposed to decode has shown us that the boundaries between possible and impossible, breakable and unbreakable, are more fluid than we once believed. But it has also pointed towards something deeper about the nature of intelligence and awareness in a universe where quantum mechanics and information processing intersect in increasingly sophisticated ways. While we cannot prove that consciousness operates according to quantum principles, the parallels are intriguing enough to warrant contemplation. Both consciousness and quantum systems seem to exist in states of superposition until observation or measurement collapses them into definite outcomes. Both seem to involve non-local connections that transcend ordinary space and time. Both appear to be fundamentally relational, emerging from interactions rather than existing in isolation. This is speculative territory, of course, and these ideas remain far from scientific consensus. But they invite us to consider whether consciousness might be not just an observer of quantum reality, but a participant in its ongoing creation. If true, this wouldn't give consciousness magical control over physical reality. Rather, it would suggest that awareness and information are more intimately connected than classical physics assumed. It would mean that the development of artificial intelligence and quantum computing isn't just changing our tools, it's revealing something fundamental about the nature of intelligence itself. The quantum computer that decoded the supposedly unbreakable password did so not through brute force, but through a form of pattern recognition that transcends ordinary computation. Similarly, your understanding of these ideas isn't just a mechanical process of data transfer. It's something more creative, more participatory, more alive. This suggests that as artificial intelligence systems become more sophisticated and quantum computers become more powerful, human consciousness won't become obsolete. Instead, it might become more important than ever, not as a competitor to these technologies, but as the awareness through which their implications can be understood and their applications can be guided wisely. The future of secrets, security, and human communication in a quantum age will be shaped not just by technological capabilities, but by the consciousness with which we approach these capabilities. The patterns that AI systems learn to recognize and the possibilities that quantum computers learn to explore will ultimately serve purposes that emerge from human awareness and intention. In this sense, consciousness itself might be the ultimate quantum password, not because it's unbreakable, but because it's the source from which all codes, all patterns, all forms of intelligence ultimately emerge and to which they ultimately return. The story continues to unfold in research laboratories and meditation halls, in quantum computing facilities and quiet moments of contemplative awareness, wherever conscious beings encounter the mystery of information and intelligence in a universe that seems to be far more participatory, far more alive than we once imagined. As we drift deeper into this contemplative space where science meets consciousness, something remarkable begins to emerge from the patterns we've been exploring. The quantum password that AI decoded wasn't just a technical achievement, it was a mirror reflecting something profound about the nature of intelligence itself, both artificial and human, both computational and conscious. Consider this: every time you understand something deeply, truly grasp a concept that was previously elusive, there's a moment of recognition that feels almost instantaneous. 1 second you're puzzled, the next you see the pattern clearly. This transition from confusion to clarity doesn't happen gradually, like filling a bucket with water. It happens suddenly, like a light switching on in a dark room. This quality of understanding, this sudden collapse from uncertainty into clarity, bears a curious resemblance to what physicists observe in quantum systems. Before measurement, quantum particles exist in superposition, holding multiple possibilities simultaneously. Then, in an instant, observation collapses these possibilities into a single, definite outcome. Now, this doesn't mean that human understanding literally operates through quantum mechanics. No scientific consensus exists on whether consciousness involves quantum processes, and correlation doesn't imply causation. But the parallel is intriguing enough to warrant gentle exploration, if only as a metaphor for how insight emerges from the depths of awareness. Take a moment to notice this quality in your own experience. When was the last time you suddenly understood something that had been puzzling you? Perhaps while listening to this exploration, or while working through a problem, or during a quiet walk when the solution to a challenge simply appeared in your mind. There's often an effortless quality to these moments of insight, as if understanding emerges from a level of intelligence that operates beyond ordinary thinking. The answer doesn't feel constructed or calculated. It feels recognized, like something that was already there waiting to be discovered. The artificial intelligence systems that learn to decode quantum passwords didn't approach the problem the way human cryptanalysts might. They didn't analyze mathematical structures or look for logical vulnerabilities in encryption algorithms. Instead, they developed what could only be described as intuitive pattern recognition, learning to perceive regularities in encrypted data that were invisible to conscious analysis. This emergence of unexpected capabilities in AI systems points towards something fascinating about the nature of intelligence itself. The boundaries between different types of problem solving often turn out to be more permeable than we expect. A system trained to recognize images might suddenly display an unexpected talent for finding patterns in financial data. A language model designed to write stories, might develop insights into complex mathematical relationships. This fluidity suggests that intelligence, whether artificial or natural, might operate according to principles that transcend specific domains of knowledge. The same fundamental information processing capabilities that allow you to understand language, recognize faces, or navigate social situations might also enable you to perceive patterns in the quantum mechanical structure of reality itself. Some interpretations suggest that consciousness might function as a kind of universal pattern recognition system, capable of detecting coherences and relationships across multiple scales of reality. This remains a speculative idea, not a proven scientific fact, but it offers an intriguing perspective on why contemplative practices sometimes lead to insights that seem to emerge from beyond ordinary reasoning. When you sit quietly in meditation or contemplation, you're not just relaxing or clearing your mind. You might be tuning into subtler levels of pattern recognition, allowing awareness to detect relationships and possibilities that are normally obscured by the constant activity of conscious thought. As you listen to this idea, notice whether there's something in your own experience that resonates with this possibility. Have you ever had insights emerge during moments of quiet reflection that surprised you with their clarity or relevance? These experiences don't require quantum mechanical explanations, but they point toward capacities of awareness that we're only beginning to understand. In the world of quantum physics, researchers have discovered that particles can influence each other across vast distances through what Einstein called the quantum entanglement effect, called spooky action at a distance. When two particles become quantum entangled, measuring one instantly affects the other, regardless of the space between them. This phenomenon has been confirmed in countless experiments, though the mechanism remains mysterious. While we cannot prove that consciousness operates according to similar principles, there are intriguing parallels in human experience that are worth contemplating. Have you ever walked into a room and immediately sensed the emotional atmosphere, even before anyone spoke? Or felt a sudden shift in your own state of mind when someone nearby was experiencing strong emotions? These experiences might have perfectly ordinary explanations involving subtle sensory cues, body language, or unconscious pattern recognition. But they also point towards something interesting about the interconnected nature of awareness itself. Some researchers speculate that consciousness might involve quantum-like properties of coherence and entanglement, though this remains highly controversial and unproven. The suggestion is that individual minds might not be as separate and isolated as we typically assume. Instead, consciousness might operate more like a field that can exhibit both local and non-local properties. This is a speculative idea that goes far beyond current scientific understanding, but as a metaphor for exploring the nature of awareness, it offers some intriguing possibilities. If consciousness does involve field-like properties, it might explain why meditation and contemplative practices sometimes seem to affect not just individual practitioners, but their surrounding environment as well. Studies have suggested correlations between group meditation and reduced crime rates in surrounding areas, though these findings remain controversial and preliminary. The mechanisms, if any, are completely unknown, and numerous alternative explanations exist for any observed effects. Take a breath here and simply notice the quality of your own awareness as you consider these ideas. Does consciousness feel entirely contained within the boundaries of your physical body? Or is there something about the nature of awareness that seems to extend beyond those boundaries? connecting you with the broader field of experience in which you're embedded. As artificial intelligence systems become increasingly sophisticated at pattern recognition and quantum computers become more powerful at exploring multiple possibilities simultaneously, human consciousness faces an interesting question. What unique capacities does awareness itself bring to this evolving technological landscape? The answer may lie not in competing with these technologies, but in cultivating qualities of attention and understanding that complement them. While AI systems excel at processing vast amounts of data, and quantum computers can explore multiple computational paths at once, consciousness brings something entirely different to the equation: the capacity for meaning-making, wisdom, and ethical discernment. Consider the practice of meditation, one of humanity's oldest technologies, for investigating the nature of consciousness itself. When you sit quietly and turn attention inward, you're not just relaxing or reducing stress. Though these benefits may occur, you're conducting a form of inner research, exploring the fundamental processes by which awareness operates. In meditation, you might notice that thoughts arise and pass away spontaneously, without conscious effort or control. You might observe that awareness itself seems to have a spacious, open quality that can hold multiple experiences simultaneously without being disturbed by any of them. You might discover that the boundaries between observer and observed, between self and environment, are more fluid than ordinary experience suggests. These observations aren't just subjective curiosities. They point toward aspects of consciousness that might be relevant for understanding how intelligence operates at the most fundamental level. If artificial intelligence systems are learning to recognize patterns that transcend their explicit programming, and quantum computers are demonstrating forms of information processing that challenge classical assumptions, perhaps consciousness itself operates according to principles that we're only beginning to discover. This doesn't mean that meditation gives you control over quantum systems or allows you to influence physical reality through intention alone. Rather, it suggests that the quality of attention you bring to any situation, including your engagement with technology, can profoundly influence the outcomes that emerge. As you experiment with this possibility in your own life, notice how the state of your consciousness affects your interactions with technology, with other people, with challenges and opportunities that arise. When you approach situations with open, relaxed awareness rather than anxious effort, do different possibilities tend to emerge? The story of the quantum password that AI decoded reveals something profound about the nature of information itself. Information, it turns out, isn't just data that exists independently in the world. Information emerges from relationships, from the interaction between consciousness and reality, between questions and answers, between the knower and the known. This understanding has implications that extend far beyond cryptography and computer science. If information is fundamentally relational, then the quality of consciousness we bring to any situation literally participates in determining what information becomes available. Think about this in your own experience. When you approach a challenging problem with anxiety and mental tension, certain possibilities tend to remain hidden, but your natural intelligence begins to operate more freely. When you relax and allow rather than force, solutions often emerge that weren't visible before. The same information was always present in the situation, but your state of consciousness determined whether you could perceive it. This principle might apply not just to personal problem solving, but to our collective relationship with rapidly advancing technologies. The artificial intelligence systems and quantum computers we're developing aren't just tools that operate independently of human consciousness. They're extensions of human intelligence, and their ultimate applications will be shaped by the quality of awareness we bring to their development and use. Some interpretations suggest that consciousness might play a fundamental role in how information manifests in quantum systems, though this remains highly speculative and unproven. The idea is that awareness doesn't just observe reality, but participate in its ongoing creation through the quality of attention it brings to each moment. If this were true, and it's important to emphasize that no scientific consensus exists on this point, it would mean that the future of artificial intelligence and quantum computing depends not just on technical advances, but on the evolution of human consciousness itself. As you contemplate this possibility, notice how it might apply to the choices you make about technology in your own life. Do you approach your devices and digital interactions with mindful awareness? Or do you often find yourself using technology unconsciously, almost automatically? The quantum password story suggests that the boundary between conscious and unconscious, between intentional and automatic, might be more important than we realize in determining what kinds of information become accessible and what kinds of possibilities emerge from our engagement with increasingly sophisticated technologies. As we approach the culmination of our journey through this landscape of quantum mechanics, artificial intelligence, and consciousness, something beautiful begins to emerge from the patterns we have been exploring. The technologies that once seemed to threaten human uniqueness, that appeared to make consciousness obsolete, are revealing themselves to be invitations to discover more profound depths of awareness. The quantum computer that decoded the supposedly unbreakable password didn't eliminate the mystery of intelligence. Instead, it deepened that mystery by demonstrating forms of information processing that transcend classical computation. Similarly, the AI systems that learned to recognize patterns in encrypted data didn't replace human insight. They revealed new dimensions of pattern recognition that consciousness itself might explore. This convergence of quantum mechanics and artificial intelligence is occurring at the same time that neuroscientists are beginning to discover quantum-like properties in biological systems. While the role of quantum mechanics in brain function remains highly controversial and unproven, some researchers are finding evidence of quantum coherence in microtubules within neurons and quantum effects in photosynthesis and bird navigation. If consciousness does involve quantum processes, and this remains a speculative idea without scientific consensus, it would suggest that human awareness is naturally equipped to understand and work with quantum technologies in ways we're only beginning to discover. But even without quantum explanations, the parallels between contemplative practices and quantum principles are worth exploring. Both involve working with uncertainty, maintaining open attention to multiple possibilities, and recognizing that observation affects outcome. Take a moment to breathe and consider how these principles might apply in your own life. When you face uncertain situations, do you try to force definite outcomes through mental effort and control? Or can you learn to rest in uncertainty while remaining alert to whatever possibilities emerge? The practice of what we might call quantum patience, the ability to hold space for multiple possibilities without premature collapse into a single option, might be increasingly valuable as our world becomes more complex and interconnected. As artificial intelligence systems become more sophisticated and quantum computers become more powerful, they're beginning to mirror capacities that contemplatives have been exploring for thousands of years. the ability to hold multiple perspectives simultaneously, to recognize patterns that transcend logical analysis, to operate from a level of intelligence that goes beyond conscious thinking. This convergence suggests that consciousness itself might be the ultimate quantum computer, not because it operates through quantum mechanics in the brain, which remains unproven, but because awareness naturally exhibits properties that parallel quantum phenomena. Consider the experience of deep meditation or contemplative prayer. In these states, ordinary boundaries between self and environment, between knower and known, often dissolve. Time seems to slow down or disappear altogether. Solutions to complex problems sometimes emerge spontaneously, without effort or analysis. While these experiences don't require quantum mechanical explanations, they point toward capacities of consciousness that we're only beginning to understand scientifically. The same qualities of awareness that allow for profound contemplative insight might also be relevant for understanding how to work skillfully with quantum technologies and artificial intelligence. Some interpretations suggest that consciousness might be fundamental to the universe in ways that transcend individual brains and bodies, though this remains highly speculative. The idea is that awareness might be a field-like property of reality itself, rather than something produced by neural activity. If true, this would mean that the development of artificial intelligence and quantum computing isn't creating new forms of intelligence, so much as revealing intelligence that was already present in the universe, waiting to be discovered and expressed through increasingly sophisticated forms. As you reflect on this possibility, notice how it might change your relationship to the technologies in your life. Instead of seeing artificial intelligence as competition for human consciousness, you might begin to see it as an extension or expression of the same fundamental intelligence that operates through your own awareness. This doesn't mean that consciousness and artificial intelligence are identical, or that AI systems are conscious in the way humans are. Rather, it suggests that intelligence itself might be more fundamental and more widely distributed in the universe than we typically assume. The quantum password that AI decoded has opened a window into a future where the boundaries between different types of intelligence become increasingly permeable. Human consciousness, artificial intelligence, and quantum computation are beginning to work together in ways that enhance rather than replace each other's unique capabilities. This integration isn't happening through direct technological merger, but through a more subtle process of mutual influence and co-evolution. As we develop more sophisticated AI systems, we're learning more about the nature of intelligence itself. As we build more powerful quantum computers, we're discovering principles of information processing that might also apply to consciousness. Meanwhile, as contemplative practitioners explore deeper dimensions of awareness, they're developing capacities that might prove essential for navigating a world of increasingly sophisticated technologies. The ability to maintain equanimity in uncertainty, to perceive patterns that transcend logical analysis, to operate from wisdom rather than mere knowledge. These capacities aren't mystical superpowers. They're natural expressions of consciousness that become available when awareness is cultivated with patience and dedication. They're relevant not because they give consciousness control over quantum systems or artificial intelligence, but because they enable us to work skillfully with these technologies in ways that serve human flourishing. Take a breath here and notice how this integration might already be occurring in your own life. When you use technology mindfully, with clear intention and present moment awareness, do you find that different possibilities emerge than when you use it unconsciously or compulsively? The quantum computer that decoded the unbreakable password might be pointing toward a future where consciousness, artificial intelligence, and quantum mechanics work together as complementary aspects of a larger intelligence that none of them could achieve alone. As we near the end of our contemplative journey through the intersections of quantum mechanics, artificial intelligence, and consciousness, let's pause to appreciate something remarkable about the story we've been exploring together. The quantum password that wasn't supposed to be decoded has revealed that the game of intelligence, pattern recognition, and understanding is far more open-ended and mysterious than we once believed. This isn't a finite game with winners and losers, where human consciousness competes against artificial intelligence for some kind of supremacy. Instead, it's what philosopher James Carse called an infinite game, where the purpose isn't to win, but to keep playing, to keep discovering, to keep expanding the possibilities for intelligence and understanding to express themselves in ever more beautiful and sophisticated forms. In this infinite game, the development of artificial intelligence doesn't diminish human consciousness. Instead, it reveals new dimensions of what intelligence can be. The emergence of quantum computing doesn't make classical computers obsolete. Instead, it expands the repertoire of tools available for exploring and understanding reality. Similarly, the cultivation of consciousness through contemplative practice doesn't compete with technological development. Instead, it provides the wisdom and discernment needed to guide that development in directions that serve the flourishing of all life. Some interpretations suggest that consciousness, artificial intelligence, and quantum mechanics might all be expressions of a deeper intelligence that operates through the universe itself, though this remains a speculative idea without scientific proof. In this view, the apparent competition between different forms of intelligence dissolves into a recognition of their fundamental unity and interdependence. As you contemplate this possibility, notice how it might affect your relationship to the rapid technological changes occurring around us. Instead of feeling anxious about being replaced by artificial intelligence or overwhelmed by quantum computers, you might begin to see these developments as invitations to discover more profound depths of your own consciousness. The infinite game of intelligence and understanding continues to unfold through all of us, through every moment of awareness, every insight, every recognition of pattern and meaning that emerges from the interaction between consciousness and reality. And so we find ourselves back where we began, with a question about the nature of secrets and the power of intelligence to reveal what was hidden. But our journey has transformed both the question and our capacity to hold it with wisdom rather than mere curiosity. The quantum password that AI decoded was never really about cryptography or computer security. It was about the endless dance between concealment and revelation, between the known and the unknown, between the patterns that structure reality and the consciousness that recognizes those patterns. This dance doesn't end with the development of more powerful computers or more sophisticated artificial intelligence. It deepens and becomes more beautiful as consciousness itself evolves to meet the increasing complexity and mystery of existence. Every time human awareness encounters something previously unknown, whether through scientific discovery, technological innovation, or contemplative insight, the universe reveals new dimensions of its fundamental intelligence. The quantum computer that solves problems beyond classical capability, the AI system that recognizes patterns invisible to human perception, the contemplative practitioner who touches dimensions of awareness beyond ordinary thinking, all are expressions of this endless unfolding of intelligence discovering itself. As you rest in this recognition, Notice how it feels to be part of this larger process of discovery and understanding. You're not just a passive observer of technological progress or scientific advancement. You're an active participant in the universe's ongoing exploration of its own nature and possibilities. The consciousness through which you're receiving these ideas, the awareness in which these words are appearing and dissolving, is itself part of the intelligence that creates and decodes all passwords, quantum and otherwise, not through magical thinking or wishful fantasy, but through the simple miracle of attention meeting reality with openness and clarity. This understanding doesn't give you control over quantum computers or artificial intelligence systems. Instead, it reveals your fundamental participation in the intelligence that expresses itself through all these forms and more. It invites you to approach the rapid technological changes of our time not with fear or resistance, but with the wonder and wisdom that consciousness naturally brings to every encounter with the unknown. The story continues to unfold through research laboratories and meditation halls, through quantum computing facilities and quiet moments of contemplative awareness. Wherever conscious beings encounter the mystery of intelligence in a universe that seems designed for endless discovery and understanding. In the quiet spaces where artificial intelligence meets quantum mechanics, researchers have begun to notice something unexpected. The algorithms that learn to decode quantum passwords didn't simply become better at breaking codes. They began exhibiting what could only be described as adaptive creativity, developing approaches to problem solving that their creators had never explicitly programmed. This emergence of unexpected capabilities points towards something profound about the nature of intelligence itself. Perhaps intelligence, whether artificial, quantum, or conscious, operates according to principles that transcend the specific systems through which it expresses itself. Like water finding its way through rock, intelligence seems to flow through whatever channels are available, creating new pathways when existing ones prove insufficient. Take a moment to notice how this principle might appear in your own experience of learning and understanding. When you encounter a challenging problem, your mind doesn't simply retrieve pre-programmed solutions. Instead, it seems to engage in a kind of creative exploration, trying different approaches, making unexpected connections, sometimes arriving at insights that surprise even you. This process of creative problem solving bears a curious resemblance to what physicists observe in quantum systems. Quantum computers don't solve problems by following a single computational path. Instead, they explore multiple possibilities simultaneously, allowing the most efficient solution to emerge naturally from the quantum landscape of potential outcomes. Some interpretations suggest that consciousness might operate according to similar principles, though this remains speculative and unproven. The idea is that awareness itself might be capable of exploring multiple possibilities simultaneously, with insights emerging through a process that resembles quantum superposition and collapse. As you contemplate this possibility, notice whether there's something in your own experience that resonates with this idea of parallel exploration. Have you ever found that solutions to complex problems seem to emerge spontaneously when you stop trying to force them through linear thinking? The story of the quantum password reveals something beautiful about the collaborative nature of discovery itself. The breakthrough didn't emerge from a single genius working in isolation, but from the convergence of thousands of researchers, countless experiments, and decades of accumulated knowledge building upon itself in ways that no individual could have predicted or controlled. This collaborative emergence reflects something fundamental about how understanding develops at the deepest levels. Like a vast resonance chamber where each contribution amplifies and harmonizes with others, the field of human knowledge seems to have its own intelligence that transcends any individual contribution to it. Recent developments in quantum cryptography exemplify this collaborative intelligence in action. Teams of physicists, mathematicians, computer scientists, and engineers from universities and research institutions around the world have been working together to understand and address the implications of quantum computing for digital security. Each discovery builds upon previous work while opening new avenues for exploration that weren't visible before. But perhaps more remarkably, the solutions they're developing often seem to emerge from the problems themselves. Post-quantum cryptography isn't just about building stronger walls around our digital communications. It's about discovering entirely new mathematical landscapes where security and openness can coexist in ways that weren't previously imaginable. The development of quantum key distribution, for instance, represents a fundamental shift from security based on computational difficulty to security based on the physical laws of quantum mechanics themselves. In these systems, any attempt to intercept a communication necessarily disturbs the quantum states being transmitted, making eavesdropping detectable by the intended recipients. This transformation from hiding information behind mathematical complexity to protecting it through quantum mechanical principles reflects a deeper shift in our understanding of security itself. Instead of building impenetrable fortresses, we're learning to create communication channels that are inherently transparent about any attempts to compromise them. As you reflect on this shift, consider how it might apply to other areas of life where security and openness seem to be in tension. In human relationships, for instance, genuine security often comes not from keeping secrets, but from creating contexts where vulnerability can be shared safely. One of the most fascinating aspects of the quantum password story involves its relationship to time itself. The encryption methods that seemed secure for decades were revealed to be vulnerable, not because of some flaw that existed from the beginning, but because the nature of computation itself evolved in ways that transformed the landscape of what's possible. This temporal dimension of technological vulnerability creates a unique form of philosophical puzzle. If future technologies can retroactively compromise today's security measures, what does this tell us about the nature of secrecy, privacy, and protection in a world where change is accelerating exponentially? The harvest now, decrypt later phenomenon we explored earlier represents one response to this temporal uncertainty. By collecting encrypted communications today, with the knowledge that future quantum computers will be able to decode them, intelligence agencies are essentially conducting attacks across time itself, using the flow of technological development as a weapon. But this same temporal fluidity also creates opportunities for protection and healing that operate across similar timescales. The post-quantum cryptographic methods being developed today are designed to remain secure even against computers that don't yet exist, creating a kind of temporal shield that reaches forward into possible futures. Some interpretations suggest that consciousness itself might operate across multiple temporal scales simultaneously, though this remains highly speculative. Some researchers even speculate that consciousness might be capable of accessing information from past experiences and future possibilities in ways that transcend ordinary linear time. Take a breath here and notice whether there's something in your own experience that points toward this temporal fluidity of consciousness. Have you ever had intuitions about future events that later proved accurate, or sudden insights about past experiences that revealed new layers of meaning? These experiences don't require exotic explanations involving time travel or precognition, but according to principles of information processing that are far more sophisticated and mysterious than we typically recognize. As artificial intelligence systems become more sophisticated and quantum computers become more powerful, they're beginning to exhibit what researchers call emergent behaviors, capabilities that weren't explicitly programmed but arose naturally from the complexity of the systems themselves. This emergence of unexpected capabilities mirrors something that contemplatives have been observing for thousands of years in the development of consciousness. Through patient practice and careful attention, qualities of awareness emerge that weren't present at the beginning of the journey. Insight, compassion, equanimity, and wisdom aren't manufactured through effort. Instead, they seem to arise naturally when the conditions are right. The parallel between technological emergence and contemplative development suggests that intelligence itself might be an emergent property that appears whenever sufficient complexity and coherence come together in the right configuration. This doesn't mean that consciousness is identical to artificial intelligence, but rather that both might be expressions of deeper principles that govern how intelligence manifests in the universe. Some researchers are beginning to explore what they call emergent cryptography, where security properties arise naturally from the complex interactions of quantum systems, rather than being explicitly designed by human programmers. These systems develop their own methods for protecting information in ways that their creators couldn't have predicted or planned. Similarly, the contemplative traditions speak of forms of wisdom and understanding that emerge naturally from sustained practice, qualities of awareness that seem to have their own intelligence and operate according to their own principles. These aren't psychological states that can be manufactured through technique. Instead, they're expressions of consciousness that become available when awareness is cultivated with patience and dedication. As you consider this parallel between technological and contemplative emergence, notice how it might apply to your own experience of learning and growth. Are there capacities or insights that have developed in your life, not through direct effort, but through creating the right conditions and allowing them to unfold naturally? The quantum password that AI decoded has become a symbol for something much larger than cryptography or computer science. It represents the ongoing integration of human consciousness with increasingly sophisticated technologies, not through replacement or competition, but through a kind of symbiotic co-evolution where each enhances the capabilities of the others. This integration isn't happening through direct technological merger, but through subtler processes of mutual influence and collaborative enhancement. As we develop more sophisticated AI systems, we're discovering new dimensions of intelligence that expand our understanding of what consciousness might be capable of. As we build more powerful quantum computers, we're uncovering principles of information processing that might also apply to how awareness operates. Meanwhile, as contemplative practitioners explore deeper dimensions of consciousness, they're developing capacities that prove essential for navigating a world of rapidly advancing technology with wisdom and discernment. The ability to remain present in uncertainty, to perceive patterns that transcend logical analysis, to operate from compassion rather than mere calculation. These aren't mystical superpowers, but natural expressions of consciousness that become available through patient cultivation, They're relevant not because they give consciousness control over quantum systems or artificial intelligence, but because they enable us to work skillfully with these technologies in ways that serve human flourishing and the well-being of all life. Recent research in human-computer interaction has begun exploring how the quality of consciousness that operators bring to technological systems can influence the outcomes that emerge. While the mechanisms remain poorly understood, some studies suggest correlations between meditative states and improved performance in complex technical tasks, though these findings remain preliminary and require further investigation. Take a moment to experiment with this possibility in your own relationship with technology. When you approach your devices and digital interactions with mindful presence rather than automatic reactivity, do you notice any differences in the quality of what emerges? As we approach the culmination of our journey through the landscape of quantum passwords, artificial intelligence, and consciousness, we find ourselves at what could be called a wisdom gate, a threshold where technical capability meets conscious discernment, where the power to decode any secret meets the wisdom to know which secrets should be revealed and which should be protected. The quantum computers and AI systems we're developing don't exist in a vacuum. They're expressions of human consciousness, extensions of our collective intelligence, and their ultimate applications will be shaped by the quality of awareness we bring to their development and deployment. This is where the contemplative dimension of our exploration becomes most relevant. The same technologies that can decode quantum passwords can also be used to enhance human understanding, accelerate scientific discovery, and solve problems that have persisted for generations. The difference lies not in the technical capabilities themselves, but in the consciousness through which they're directed. Some interpretations suggest that consciousness might play a fundamental role in determining how advanced technologies develop and what kinds of capabilities emerge from them, though this remains a speculative idea without scientific consensus. The suggestion is that the intentions, values, and quality of awareness of the researchers, developers, and users of these technologies might influence their evolution in ways that we're only beginning to understand. Whether or not consciousness directly influences technological development, it certainly shapes how we choose to use the capabilities that become available. The quantum computer that can break any encryption could be used to compromise privacy and security, or it could be used to develop new forms of protection that are more robust and equitable than what came before. As you contemplate your own relationship to rapidly advancing technology, notice how the quality of consciousness you bring to these tools affects not just how you use them, but what kinds of possibilities you perceive in them. Do you approach technology with anxiety and resistance, or with curiosity and wisdom? In the deepest reaches of our exploration, we encounter a beautiful paradox that brings us full circle to where we began. The quantum password that AI wasn't supposed to decode has revealed that the very concept of supposed to, of fixed limitations and permanent impossibilities, might itself need to be decoded and understood in new ways. Every security system, every encryption method, every attempt to create permanent barriers between known and unknown ultimately depends on assumptions about what kinds of intelligence and what forms of computation are possible. But intelligence itself seems to be far more creative, adaptive, and mysterious than any of our assumptions about it. This suggests that the relationship between secrets and revelations, between hidden and revealed, between protected and exposed, might be more fluid and dynamic than we typically recognize. Instead of thinking in terms of permanent security or absolute vulnerability, we might need to develop approaches that embrace the ongoing dance between concealment and disclosure. Some interpretations suggest that consciousness itself might be engaged in this same dance at the most fundamental level, though this remains highly speculative. The idea is that awareness is constantly involved in processes of hiding and revealing, forgetting and remembering, creating mysteries and solving them in an endless cycle of discovery and understanding. As you rest in this recognition, notice how it applies to your own inner life. Aren't you constantly involved in processes of discovering things about yourself that were previously hidden? Aren't insights and understanding emerging all the time from depths of awareness that you didn't know existed? This inner process of discovery and revelation might be the most fundamental expression of the intelligence that also manifests through quantum computers, AI systems, and all other forms of information processing. The password that gets decoded, the pattern that gets recognized, the mystery that gets solved, all are expressions of consciousness encountering itself in ever new forms. And so we find ourselves back in the realm of wonder where our journey began, but transformed by everything we've discovered along the way. The quantum password that AI wasn't supposed to decode was never really about technology or cryptography. It was about the inexhaustible creativity of intelligence itself, the endless capacity of consciousness to surprise itself with what becomes possible. This creativity doesn't belong only to artificial intelligence or quantum computers. It's the same creativity that operates through your own awareness right now, the intelligence that's making sense of these words, connecting ideas and perhaps discovering insights that weren't there when you began listening. The future of artificial intelligence and quantum computing won't be determined solely by technical advances or computational capabilities. It will be shaped by the consciousness through which these technologies are developed, deployed, and integrated into human life. And that consciousness includes your own awareness, your own capacity for wisdom and discernment. Recent developments in quantum computing and AI are creating possibilities that were inconceivable just a few years ago, but they're also revealing the enduring importance of qualities that no technology can replicate: wisdom, compassion, ethical discernment, and the capacity to hold complexity with patience and grace. These aren't optional extras that we can develop after we've mastered the technical challenges. They're essential capacities that need to be cultivated alongside technological advancement if we're going to navigate the increasing power of our tools with wisdom rather than mere cleverness. Take a final breath and notice how this entire exploration has unfolded within the space of your own consciousness. The ideas we've shared, the connections we've made, the questions we've raised, all of this has emerged through the mysterious process by which awareness encounters information and transforms it into understanding. This process of conscious understanding is itself a form of quantum computation, not in any literal sense, but in the deeper sense that consciousness naturally operates with superposition, entanglement, and collapse in ways that parallel what we observe in quantum systems. Your ability to hold multiple possibilities simultaneously, to make connections across vast networks of information, to arrive at insights that transcend logical analysis. These are expressions of the same intelligence that manifests through our most sophisticated technologies. The quantum password that AI decoded points toward a future where the boundaries between human consciousness, artificial intelligence, and quantum computation become increasingly permeable and collaborative. not through merger or replacement, but through recognition of their common source in the fundamental intelligence that permeates the universe. As we reach the gentle close of our exploration through the quantum realm, where artificial intelligence learned to whisper secrets that were never supposed to be heard, take a moment to appreciate the profound transformation in our understanding that has unfolded. We began with a simple question about an unbreakable password, but we've discovered something far more magnificent: the fluid nature of impossibility itself. The quantum password that AI decoded was never really just about cryptography or computer security. It was a mirror reflecting the endless creativity of intelligence in all its forms, from the quantum computers exploring multiple realities simultaneously, to the artificial minds recognizing patterns invisible to human perception, to the consciousness through which you've been receiving and understanding these ideas. What we've witnessed is not the triumph of technology over human intelligence, but the revelation that intelligence itself operates according to principles far more mysterious and beautiful than we ever imagined. The boundaries between artificial and natural, between quantum and classical, between observer and observed, are not walls to be defended, but membranes through which understanding flows in both directions. The future that emerges from this convergence of quantum computing and artificial intelligence will be shaped not just by computational power or algorithmic sophistication, but by the quality of consciousness we bring to these developments. The same awareness that allowed you to follow this contemplative journey, to make connections across vast networks of ideas, to arrive at insights that transcend mere logical analysis, is the intelligence that will ultimately guide how these technologies serve the flourishing of life itself. In the end, perhaps the most profound password that has been decoded is the illusion that consciousness stands separate from the intelligence that permeates the cosmos. We are not observers of a quantum universe operating according to mysterious principles. We are expressions of those principles, participants in the endless unfolding of intelligence, discovering itself through every form it takes. The questions we've explored together will continue to evolve and reveal new dimensions of understanding long after these words fade from memory. But the awareness through which you've encountered them remains, forever open to the next impossible thing becoming possible, forever present to the mystery that dances at the heart of existence itself. Until our paths cross again in the vast quantum field, where all possibilities coexist, may your consciousness remain forever curious about the nature of observation and reality. If this exploration has awakened your interest in how awareness itself might participate in the quantum realm, I invite you to continue this journey with Quantum Observation Just Got Real. Here's how to direct your energy, where we dive even deeper into the practical implications of conscious observation in a quantum universe. Implications of conscious observation in a quantum universe.